Hello, I'm Laur Hesse at the Massachusetts Institute of Technology, and you're listening to Today I Learned Climate. So get this. Some of the climate-warming carbon dioxide that we create when we burn fossil fuels is naturally absorbed by the Earth. In other words, every day, plants, trees, soils, even the oceans are taking some of our climate pollution out of the atmosphere. But how much? Well, today we're answering that question from Howland L. of Washington, who wonders, how much carbon dioxide does the Earth naturally absorb? So let's begin by quickly covering how the Earth absorbs carbon from the atmosphere. Okay, so you probably have heard of photosynthesis, when plants and algae take CO2 out of the air and pick it apart for its carbon, which they use to grow. That's one way the Earth absorbs carbon. Another way is through the oceans. CO2 also mixes with and dissolves into ocean water. But that carbon doesn't stay out of the air forever. Here to explain is Professor Daniel Rothman, who studies the Earth's carbon cycle at the MIT Department of Earth, Atmospheric, and Planetary Sciences.
I like to think of the carbon cycle as a loop between photosynthesis, which takes CO2 out of the atmosphere and oceans, and respiration, which describes all the metabolic processes that organisms, ranging from microbes to mammals, use when organic carbon is oxidized and reconverted to CO2.
Yeah, it's reconverted to CO2 when the plants and the animals and humans that eat them die and decompose and their carbon binds with oxygen and becomes CO2 again, or when those animals breathe out, right? Like we breathe out CO2. This is the carbon cycle. It's a lot like the water cycle, which you probably already know about. Water falls as rain and then evaporates and rises back up into clouds. You know how some parts of the water cycle happen daily, like rainfall and evaporation, and some parts of it take hundreds, thousands, millions of years, like forming glaciers and ice sheets? Well, that's kind of similar with carbon, too.
An important thing to realize is that once CO2 is converted to organic carbon by a plant, its reconversion to CO2 occurs at a vast range of timescales, ranging from minutes to millions of years.
Here's an example. When plants and algae and animals die and then get buried deeply enough over millions of years, they become subject to incredible pressures and temperatures. And eventually, this pressurized organic matter becomes carbon-rich coal, oil, and gas trapped in rocks underground.
In fact, about 0.1% of carbon enters the rock cycle. Some is simply locked up in rocks until either it's brought back to the surface by us and becomes fossil fuel, or it re-enters the atmosphere via volcanism, or is uplifted on the continents by plate tectonics.
But for carbon to be pulled out of the atmosphere and buried and pressurized into fossil fuels and then naturally re-enter the atmosphere in this way, it takes hundreds of millions of years. In fact, some coal deposits have been locked up underground for more than 300 million years. So these are the different speeds of the carbon cycle. And despite all these different speeds, the natural carbon cycle has more or less been in balance.
Roughly speaking, the natural cycle takes up and puts out about 100 gigatons of carbon every year into the atmosphere. A gigaton is 1 billion tons.
100 billion tons of carbon. Whew. All right, so I'm going to subject you to some math and chemistry just for a quick moment. Because when that carbon binds with oxygen in the air, it becomes carbon dioxide, right? CO2. So if you want to know the amount of CO2 flowing through the carbon cycle or flowing in and out of the atmosphere, you have to weigh the oxygen atoms along with those carbon atoms. And that would make it 350 billion tons of carbon dioxide. You're probably like me in that you find it really hard to even begin to visualize a number like 350 billion tons, but here's a stab at it. So the weight of all of the buildings in New York City is about 750 million tons. Yeah, someone estimated it. So the carbon dioxide that the Earth absorbs and releases every year to and from the atmosphere weighs about 500 New York cities every year. So that is your answer, Howland. It's a lot. But how about the carbon that humans are adding when we dig up and burn those fossil fuels? I mean, it's enough to influence our whole climate system, so it must be a lot of CO2, right?
Human-based emissions are about an order of magnitude less, or about 10% of the natural flux.
Wait, so all this extra CO2 that we're so worried about, that we've been told again and again are dangerous for us and our planet, they're only a tenth of what the Earth naturally absorbs every year?
The average person might think that 10% additional CO2 emissions is a minor perturbation of the natural cycle, but it accrues over time.
Yeah, the natural cycle can't absorb CO2 quickly enough to remove all of this extra carbon. Think about a bathtub where the water coming out of the spout is faster than what's going down the drain. The water starts building up in the bathtub, right? Same as with carbon. In fact, about 40% of our emissions just stick around in the atmosphere, building up year after year.
What we're doing with taking coal and oil and gas out of the ground is essentially speeding up a natural process. Geologic processes such as plate tectonics would naturally bring that carbon back up, but on a much slower timescale, over millions of years. Now we're releasing all that carbon over a few hundred years.
In fact, since humans have started burning fossil fuels at a large scale, we've managed to add about 300 billion tons of carbon to the atmosphere total. That is roughly triple the size of the natural carbon cycle.
Eventually, that extra CO2 would be naturally diminished by processes involving the rock cycle, but it would take on the order of 100,000 years.
So once we've opened up a shortcut in the natural cycle, there's no natural shortcut back. If we don't pull the extra CO2 out of the atmosphere, we'll have to live with it and the warming that it brings, perhaps for thousands of generations. And that makes this a uniquely important time in our planet's history, because we can still stop shortcutting the carbon cycle. By keeping fossil fuels in the ground, that carbon will be locked up in the slowest parts of the carbon cycle. And there are other ways to keep carbon in that slow cycle, by pumping our carbon emissions in the ground, or by locking carbon up in rocks or the deep ocean. To learn more about those methods to work with this slow path of the carbon cycle, check out our show notes on tilclimate.mit.edu. So thank you again for this question, Howland. I hope that you learned as much from this episode as we did. And for all of our other listeners, if you have a question that you want to ask us, please do. Visit climate.mit.edu/ask or leave us a voicemail message at 617-253-3566. We'll be releasing answers as episodes here on TIL Climate, as well as at climate.mit.edu. We always love hearing from our listeners. Feel free to leave us a voicemail message at the number we just mentioned, or email us at climate@mit.edu. We'd love to hear about who you are and what you're working on and why you listen to the show. TIL Climate is the climate change podcast of the Massachusetts Institute of Technology. Aaron Krol is our writer and producer. David Lishansky is our audio producer. Michelle Harris is our fact checker. Sylvia Scharf is our climate education specialist. The music is by Blue Dot Sessions, and I'm your host and executive producer, Laur Hesse Fisher. A big thanks to Professor Daniel Rothman for speaking with us, to Andrew Moseman, who did the original reporting for this episode, and to Howland L., and all of you, our listeners, for your climate curiosity.